All right, now we've defined eigenvector and eigenvalue, and that eigenvector and eigenvalue comes from this sort of equation: ax equals lambda x. So A is the matrix. It's going to be a square matrix. X is a vector, and lambda is a scalar number. It could be complex. So X is called the eigenvector, and lambda is called the eigenvalue. Okay, eigenvector and eigenvalue. Okay, so we've seen that some matrices have eigenvectors, eigenvalues, but if they're not too common, they really aren't that interesting. Now, it turns out that in fact every matrix has an eigenvalue. Now, we've seen already that if the matrix is singular, it has eigenvalue 0. But in fact, any matrix, even if it's non-singular, has at least one eigenvalue. All right, and here's the proof. We're going to use this idea of polynomials of matrices. Okay, so let me start with vector x. I can multiply that by a squared, by a cubed, all the way up to an. Now, what do we have here? X is a vector, ax is a vector, a squared x is a vector, all the way up to a to the nx is a vector. And let's suppose that a has size n by n. How many vectors do you have here? Well, if you start here, you have 1, 2, 3, all the way up to n, and you have one more, so you have n plus 1 vectors. What does that mean? N plus 1 vectors in Cn. That should ring some bells. The dimension of Cn is n, so you can't have more than n linearly independent vectors. These vectors are linearly dependent. Okay? So if they're linearly dependent, we can form a linear dependence relation. Here's our linear dependence relation. I don't know what the constants are, but I do know that there is a linear dependence relation. And some of these must be non-zero because I have to have a non-trivial linear dependence relation. Okay. Now, some of these a's may be 0, but they can't all be 0. So let's just take the terms up to the largest am. So that's what this polynomial is. And we can always divide this polynomial by the value of am, so we can assume that am is equal to 1. All right, now if you remember from theory of polynomials from high school, you can factor any polynomial over the complex numbers. Okay, and if the leading coefficient is 1, that means that all the coefficients of x among the factors are 1. Okay, so you've seen the quadratic formula. If you have x squared plus bx plus c, you can factor that as x minus r1, x minus r2. Okay, as long as the leading coefficient is 1, I can factor the polynomial into terms like this. Okay, so what can we do with that? Well, let's rewrite our linear dependence relation in terms of this factored form. Okay, we have a linear dependence relation. This is a polynomial. We can write this as this matrix polynomial applied to the vector x. We can factor this matrix polynomial. And what we end up with is that the 0 vector is equal to a product of matrix factors applied to a vector x. Now, just notice something is that we could rearrange these factors arbitrarily. It really doesn't matter. I can write x minus 1 times x minus 2, or I could write x minus 2 times x minus 1. We could do the same thing here. We could rearrange these arbitrarily. Okay, now notice what we have here. We have a minus bkin times, I can consider this as a vector. Okay, so I have a minus bki times some vector. And we're going to define that vector as z. All right, now it's possible that z is 0. If z is 0, then chop off this one and take a minus bk minus 1 and take that one. At some point, you know that x is non-zero, so there must be a first place where you end up with a 0 vector. So just keep on going till you get the 0 vector and then go back 1. So here we have a non-zero vector, and a minus bki times z is equal to 0. Okay. Now there's this derivation here, but what I would just say is you have a minus bki times z. That's the same thing as az minus bk times iz, but that's the same thing as az minus bz. And notice that A is a matrix, B is a number, and we know that this is equal to 0 because we found that. So that's equal to 0. If I take the bz to the other side, I just get az is equal to bz. All right. That means that z is an eigenvector and b is an eigenvalue. Okay. Now notice we could rearrange the terms and find other eigenvectors, eigenvalues. Now this seems very involved. Let's look at an example to see how it works. All right, so it's a long computation, but it's just step by step. Suppose you have this matrix A and this vector x. Okay, now how did we start out? We started out by taking x and multiplying it repeatedly by A. So if I take x and then take ax, and then take the result of ax, multiply it by a again, I'll get a squared x. Multiply it by a again, I get a cubed x, all the way up to a to the 5th x. If you do that using Sage, don't do it by hand, you'll get this set of 6 vectors. These 6 vectors must be linearly dependent, okay, because they're in C5. So let's go ahead and find a linear dependence relation. Take the matrix, row reduce, and this gives us a way to find linear dependence relations. These are all free variables, so I can choose these free variables arbitrarily. Okay, so we could make a simple choice. So the choice that he chose is, this is an arbitrary choice here. Don't think that this is anything special. He just chose these arbitrarily. Okay. Now if you make this choice, x3 equals minus 8, x4 equals minus 3, x5 equals 1, and x6 equals 0, that will determine x1 and x2. Right. So by determining x1 and x2, you plug those values in. Here's the minus 8 here, the minus 3 here, the 1 here, the 0 here, and these two were obtained by solving these two equations here. Right, this is x1. x1 is going to be equal to 2x3 minus 6x2 plus 14 what is it? That's x2, x3, x4, x5. It's plus 14x, x5 minus 30, x6. Okay, so we can solve for all of these coefficients and obtain the coefficients in this linear dependence relation. Okay? All right, now what do you do? Now you need to factor this polynomial. Okay, you might have to use some software to do this. So if you can factor this polynomial, then we have a matrix identity where we replace the x with the vector, with the matrix A, and we replace the constants with the constants times the identity matrix. Okay. All right, now we do as described before. Start with our vector x and multiply by these matrices one by one. If I multiply vector x by matrix A plus I5, I get another vector using Sage. If I multiply that result by A minus 2I5, I get another vector. If I multiply by A plus 2I5, I get 0. So what does that mean? That means that A plus 2I5 times this vector here gives me the 0 vector. All right, that means that this vector, if I compute this vector, that means that A plus 2I5 times this z is equal to 0. And that means that if you rearrange this, that's the same as AZ plus 2I5z equals to 0, which is the same thing as saying AZ is equal to minus 2z. Okay, because the I5z just gives me a z. AZ equals minus 2z. We found an eigenvector with a particular eigenvalue. Okay, a little bit complicated computation, but if you look at this example, go step by step, I think you can do it.